log with a base greater than 1. Let's say natural log x. See, there is nothing here. And the other possible shape is this. For example, let's say log base 1/2 of x. See, there is nothing here, which means this function has restrictions. This function is not defined everywhere. It's not a nice function, quote unquote, like the polynomial functions, like the absolute value function. It's not. I have to worry about its domain. It's not defined everywhere. It's only defined between 0 and infinity. Between 0 and infinity. And not even at 0, because it's a vertical asymptote there. So then, when we solve log equations, we have two options. Two options when solving log equations. I'm not telling you which option to pick, but you have to pick one or the other. One option is check solutions in the original equation. Second option is state domain. You know me, I'm lazy when it comes to plugging back in, and I may forget, who knows. I prefer stating a domain. You can say, no way, I'm not going to state a domain, I don't like it. But I promise to check solutions. That's fine by me. I don't like going back and checking solutions. I prefer domain. But you choose whatever you want. But you don't have to be consistent. You can solve the first problem with checking solutions and the second one with stating a domain. But you always have to use one or the other when solving log equations. Okay, so let's take a look. We are on page 515. And let's start with problem 60. 515. Log base 2 of 4x plus 1 equals 5. Can anyone tell us how to find the domain of this function? We had examples last time, if you want to go back to your notes, or not equal to.
Or the greater than 0.
Perfect. It cannot even be 0 because it's a vertical asymptote. Good. Very good. That's all I needed. So 4x greater than -1, x greater than -1/4, domain -1/4 infinity. Excellent. So let's suppose I solve the equation and I get that I get x equals -3. What will you say? Acceptable or not? No, not acceptable. -3 is not here. Let's say I solve the equation, I get x equals 5. Acceptable or not? Yes, because it's in the domain. Very good. So let's go back. I'm going to copy it. You don't have to copy it again. I just ran out of room, of course. Good. So what was the most important concept that I consider the most important concept in this chapter? We said that any log, excellent. Any log equation can be changed into an exponential one. Okay, let's do it. Exactly. 2 to the 5th equals 4x plus 1. Awesome. We always start with a base, going counterclockwise. 2 raised to power 5, not 2 times 5, careful. 2 raised to power 5 equals 4x plus 1. In certain log equations, maybe I should correct myself, in certain log equations, there is no need to change them to exponential. But an log equation like this one can always be changed into an exponential. But in certain situations, I'll give you examples in a minute, there's no need to change it. It's too easy. Any questions on this so far? Okay, so this is, I know it's 32 equals 4x plus 1. It's linear now. I subtract 1. I get 4x equals 31, or x equals 31 over 4. Of course, I have to ask myself, does it work? because I know I'm solving an equation with a function that has problems. Does it work? What do you think? Yes, because it's a positive number. Furthermore, it's a number greater than negative 1/4. That's all we needed. So I will say yes. Good. Feel free to choose any problem you'd like. 49 through 92.
80?
Say it again. 80. Excellent. Here it is. Same page. 515 log of 2x minus 1 equals log of x plus 3 plus log 3. It's not a must, but I recommend the two functions with x to be on the same side. So I will rewrite log 2x minus 1 minus log x plus 3 equals log 3. This is a number. I'm not going to state any restrictions on log 3. It's just a number. So can anyone give us the restriction for the first function? What will I have to write for the first function to exist? Perfect. What will I have to write for the second function to exist? Excellent. There is no restriction for this, right? This is just a poor number. Now let's discuss the two restrictions, because obviously we are talking about the common what? Excellent. I need to find that territory that in which both functions exist at the same time. Okay, perfect. So this inequality means x greater than 1/2. I move 1 and divide by 2. This one means greater than negative 3. For the first example, I think we should graph. So let's graph and see what happens. So 0 is in the middle, negative infinity, infinity. Greater than 1/2, let's say this is 1/2. And greater than negative 3, let's say this is negative 3. Well, you know I don't care for units. I just want to make sure that I put them in the correct order. So now I need to find or choose the domain that makes both functions exist. And I'm ready. What is the common domain? Exactly. It's where I see pink and green at the same time. If I pick here, only one of them exists. If I pick here, none. But if I pick anywhere between 1/2 and infinity, they will both exist. Great job. Now I need to condense. Anyone remembers how to condense the left-hand side? How do we condense the left-hand side? It's a difference of 2 logs. Where does it come from? What do I have to have in order to get a difference of logs? Say it again. Yes, log applied to a fraction. Excellent. But log. Okay, so the left-hand side is log, and I forgot to ask you, I don't see the base here. What is the base? Exactly. Log has base 10. Very good. So can anyone condense the left-hand side? If it has minus in front, it has to come from the denominator. If it has positive in front, it has to come from the numerator. We learned that last time.
On the test, it say condense, right?
No.
No, it is say.
No, solve for x. Yes, yes, yes. Okay. In this particular case, this is a log equation, but here's why we don't need to change it into an exponential. So let's do this together. 2 logs are equal, and they have the same base. What has to happen to the quantities that we apply log? Of course. By the one-to-one property, they have to be equal. So from here, I have 2x minus 1 over x plus 3 must equal 3. So in this particular case, so maybe I should correct myself a little bit in the sense that not all log equations can be changed, but there is no need to change all log equations into exponential. This was too easy. There was no need to change it into an exponential. So one more time, please do not cross out the log. Do not say that I simplify both sides by log. That's not what we're doing. We're only thinking two logs are equal and they have the same base. You will always have the same base in this class, because otherwise it's not a big deal. We can change the base. So two logs are equal and they have the same base. The quantities we apply log to must be equal to each other. Okay, so now this is coming back from our past. What do I do now, and what type of equation is it?
Multiply with x plus 3.
Correct. Or the same thing. It's really the same thing. 2x minus 1 equals 3x plus 9. Now look one more time. Let's look at this problem one more time and see how many levels, how many steps. A lot. So first of all, what did I do? I moved the x's on one side, the logs with x. Then I stated domain for each. Then I solve for the common domain. I determine the common domain. Then I condense the left-hand side into log applied to a quotient because I had a difference of logs. Then I thought, okay, how can this happen? Well, it can only happen when this equals this. Then now it's a proportion. I cross multiply. Now I have a linear equation to solve. For more than a minute, I only listed the operations we went through. It's not a trivial problem, right? So I move 3x and I move 1. So this is negative x equals 10, so x equals negative 10. And after all this effort, what do we conclude? No solutions. Because negative 10 is not in the common domain. You cannot plug it in any of the functions. The log will not even exist. So the equation has no solutions. Problem 70. Any questions from me before we move on? 70. Log base 6 of x plus 3 plus log base 6 of x plus 4, they say equals 1. Okay. It's a log equation. I have to worry about domain, or I make myself a note. I have to go back and check back to the original problem. Okay.
I'm sorry. What is this called? What are we learning right now?
This is log equations. Last time we looked at we looked at exponential equations, and we left this part for today.
Log equation.
Yes, second half of 4.4. 4.4.
Thank you.
Good. So then, what do I have to write for the first one to exist? For the second one to exist. This one says greater than negative 3. This one says greater than negative 4. So let's do this together. Here is negative 3, and here's negative 4. Negative 3 to your right, negative 4 to your right. I need the common territory. Negative 3 to your right, and negative 4 to your right. What would be the common territory?
Negative 3.
Excellent. Common domain, negative 3 to infinity. Excellent. Do we all agree with negative 3 to infinity? Do you need me to graph? Please say graph and I'll graph. Is this clear? Okay, very good. So now let's condense the left-hand side. How do I condense the left-hand side? It's a sum of logs. So then, yes, so I have to write log base 6 of x plus 3 times x plus 4 equals 1. Now this, I will definitely change into an exponential equation. No question about it. So how do I write the exponential equation that replaces this log equation?
The first power.
Exactly. We always start with the base. Base raised to the first power equals this. 6 to the first power equals x plus 3 times x plus 4. Okay, now what do I do with this? What type of equation is it? How many solutions I expect? And what do I do with it? This is again from our very, very long time ago. What do I do? Yes?
What is it called?
Distribute.
Oh, okay.
FOIL. Very good.
Yeah.
X squared plus 3x plus 4x plus 12 minus 6 equals 0. It's quadratic. X squared plus 7x plus 6 equals 0. And I'm hoping, one of my students said last night, you're doing your little math very fast. But actually, I shouldn't say this, but I will, because I started. One of my students who became a very good friend of mine, she calls me Little Math. She calls me up and says, hey, Little Math, how are you doing? And I said, Justine, I'm okay. How are you? She will be very proud that I mentioned her. Good. So
X plus 6 and X plus 1.
x plus 1, x plus 6. So we have two options, x equals and x equals. -1, -6, with a big question mark. Which one, if both 1, 2,
Negative 1 would work.
very good. -6 is not in -3 to infinity, but -1 is. So please look through anything and choose anything else. Let's do one more and then we'll move on, or whatever. If you need more, I'll do more. Yes?
Could you just refresh me one more time? Is it A? That A is backwards now, right? So A
This?
squared, yeah.
So x squared plus 3x plus
just
4.
4 and just
Yeah.
Oh, okay, you just
Yeah, and then I subtracted 6
all right.
because I have to clean it up and then factor.
You're thinking of if you had X plus 3 squared.
Yeah.
Right? And that's when you do the
Reverse thing.
Yeah.
Okay, so we just basically just multiply.
you just did FOIL. I knew where you were going.
100 years from now, when I'm going to call Charisse at 2 o'clock in the morning, I'm going to say, a binomial squared is how many terms? How many again?
Someone say it's not required for me to know at this point, right? I know you're going to tell me.
She's going to hang up on me, but that's okay. Good. Do we need more log equations? If not, we move on to applications. The last section of this chapter.
Does applications have anything to do with log equations?
Of course, tons.
Oh. Can you do one
Because
more then?
everything will be changed into an equation, of course. Yes,
Just one.
anything you want, please pick. Pick, you pick. Don't blame me. Charisse is speaking.
Probably should leave the class.
Oh no, I'm kidding. I'm kidding. I'll guard you with my life if they want to do anything to you.
You said through which number?
Anything from 49 through 92.
Okay. This is 78.
78 it is. 78. Where are you, 78? I see it. So log 5x plus 1 equals log 2x plus 3 plus log 2. I don't see the base. Let's clarify that the base is. Very good. Base 10. Okay. So I see, bless you, I see 2 logs with x. I'll make it 1. Let's see if it works. So I see 2 logs with x, so I'm going to move them to one side. Log 5x plus 1 minus log 2x plus 3 equals log 2. Do not condense. This is very important. Do not condense and then state the domain. You have to state the domain on the raw equation before you condense. It's not going to be the same domain. Okay, so please give me the inequality for the first one to exist. Perfect. For the second one, good. So then from here I have greater than negative 1/5, and here greater than negative 3/2. Now, with these numbers, it may be better if we graph, right? So this is, oops, I didn't mean to write 0 over there. So 0, negative infinity to infinity. And negative 3/2 is bigger than negative 1/5, right? So this is negative 3/2. I meant to the left, bigger in the negative sense. And negative 1/5 is here. And I have to choose both blue and red. So what will be the common domain?
Negative 1/2.
Yes. So the common domain is negative 1/2 to infinity.
You mean 1/5.
Okay.
Of course. She's so powerful tonight. Just don't tell me to jump from the Empire State Building, because I may do it. Okay, good. So now let's condense the left-hand side. How do we condense the left-hand side? What do I have to write first? This is very important. What I write first. I have to write log. Yes, I have to write log of what? Five x plus 1. Is that clear? Because it's minus. Yes. Equals log 2. Again, this is a nice situation in which there is no need to change this into an exponential equation. Why? Because both sides have log. Two logs are equal. They have the same base. It's crucial. Then what has to happen to these quantities? In other words, I'm asking you, can log 15 be log 2?
No.
Right? So this cannot be 15 and this is log 2. This cannot be log 15 equals log 2. Agreed? It's not going to work. So what has to happen to these two quantities? They must be equal to each other. So 5x plus 1 over 2x plus 3 equals 2, or 2 over 1, to refresh my memory on the fact that this is a proportion. And then I will cross multiply. Which in a way sometimes is easier than solving a quadratic equation, right? So then we have 5x plus 1 equals 4x plus 6. Because now this became linear. So I move 4x and I move 1. So I get x equals 5. Does it work? Yes, because the domain, the common domain was negative 1/5 to infinity, and 5 definitely fits in there. So I will say yes. Any questions?
Yeah, I have one.
Yes,
So
please.
5, that one is yes, but the last one was no. And the answer was, oh, no. Wait a minute. X equals negative 1, so no, then. No. Yeah, the answer was x equals negative 1, and we said it was, no, it was negative 10. I'm sorry, I'm looking at the wrong thing.
Is that okay?
No, it's not. Because it says x equals, yes, it is. Okay, yeah.
Is that okay?
It is, yeah. Negative 10 is on the left-hand side. I was thinking positive 10.
Okay, very good. Last section, 4.5, applications. They are not trivial, but I wouldn't say they're super difficult either. They are very similar, with the exception of one, and everything else is kind of similar. Okay, so we already looked at two applications before. Number one was interest compounded n times per year. Interest we did that. We looked at something like that. The second application was continuously compound interest. Compounded interest. All formulas in this will be given to you. You don't have to memorize any of this. Now, the other three that we are going to look at here right now are exponential growth. What grows exponentially? Bacteria grow exponentially. Rats, mice, fish, people, rabbits, birds grow exponentially. Next application, exponential decay. When and how and what is this? Refers to different applications, but main application here is a radioactive substance. A radioactive substance, and we looked at one example with a Chernobyl cesium, I don't remember, 137, that was in the atmosphere, and people couldn't go back home because it was damaging to their health. So initially in 1986, it was a big explosion, and in atmosphere they had blah, blah, blah. But over time, 80 years later, 70 years later, it decreased. That's exponential decay, when the mass of a radioactive substance decreases in time. So for example, if we have in an enclosed container, let's say, we cannot breathe that, right? Enclosed container, some radioactive substance, and let's say we have 100 milligrams. And the half-life, let's say, is 2 days. I have 100 milligrams. How many will I have in 2 days later? How many will I have 2 more days later? How many will I have 2 more days later? And so on and so forth. Okay, that's the exponential decay. And the last one is logistic growth model. Logistic growth model. None of these you have to memorize. They will be given to you in the problem. Okay, so let's start with the exponential growth. There are not very nice problems in here with exponential growth. So I'm looking at the review at the very end on page 538. I did this problem with the previous class, and I really enjoyed it. So let's see if you enjoy it. So 86 on page 538. According to the U.S. Bureau of the Census, in the year 2000, there were 35.3 million residents of Hispanic origin living in the U.S. By 2010, the number had increased to 50.5 mil. The exponential growth function is given to us is a of t equals a0 e to kt. This is the exponential growth model. It's given to us in the problem. Describes the U.S. Hispanic population A in millions. So I make a note, of course, in millions. T equals, it says T years after 2000. T equals 0 represents the year 2000. So T is the time in years. Let's analyze the model for a moment. So this is the number of people. In this case, Hispanic origin. This is the initial population, initial or original. from the moment we start counting. And we started counting in 2000. K is the growth rate. And T, time in years. We've seen this before. This was the exact model for the continuously compound interest, where we had the amount of money, P the principal, interest rate, time T in years. Okay. So let's go back to the problem and let's analyze what we're given again, and let's talk about the information that is given to us. Ready? In the year 2000, 35.3. In the year 2010, 50.5. What are we given here? Yes, but what is this? When we are told in the year 2000, 35.3, in the year 2010, 50.5. Say it again. Yes, but what is this? Say yes. Time and amount. What does this, when I'm given the time and the amount, what is this? Not yet. So what is this information called? And the same thing here. What are these? Correct?
The point?
Exactly.
Okay.
Can anyone give me the first point, please? Excellent. It's ordered pairs, right? So remember, this is the independent variable, which is time, and this is the number of people. So when I'm told time, comma, people, twice, time, comma, people, I'm given two ordered pairs. So I cannot use the name of the year. So then give me the first point, and then please give me the second point. I cannot use the name of the year. Yes? Of course.
0.
Good.
Oh,
Exactly.
I see.
So these are the two given points to us. They are not telling us that they are points, but we have to identify them correctly. Okay, now, furthermore, what does this mean? When time is 0, A of 0 is 35.3. Remember, in any point, this is the hidden information. A of 0 is 35.3. This is what we are told here. Can anyone tell us what we are told for the other point? Yes. We have to be able by now to identify this situation. This is true for any point. Remember, any point is x comma what? F of x. It is y, but we have to be to understand that this is not just any x comma y, but it's x comma the function value at that x. Okay, perfect. So now let's put this in slowly and surely in the function. I want to put this information here. The left-hand side, please dictate. I'm talking about this just now. Then about this in a minute. This one.
So, A times, oh no, T.
What is this?
A is 0.
35.3 equals A0, which is the initial when we started counting, times E to K times, I'm talking about this point. Exactly. That's why we wrote this. When time is 0, A of 0 is 35.3. So then, now let me make sure. We are trying to develop the model from the given information. I have two unknowns. One unknown is A0, and the other unknown is K. A0 is the initial population, and K is the growth rate. I'm trying to find them so then I can answer any question about the model. I don't have those two yet. Okay, so then, how much is K times 0? How much is e raised to 0? Please don't say 0. 1. Excellent. So then what is the original value or original number of people from the moment we counted them first? Exactly. You can say, wasn't that clear from the very beginning? Yes, but I wanted to illustrate how to plug the point in so that it's easier for the second one now. So here's what I know so far. I know that a of t equals 35.3 times e to kt. This is what I have so far. I determined the original number of people, but I still have k to determine. Now I need to use the second point and plug it in. Slowly tell me what to write when we use the second point to plug it in. Yes, 50.5 equals 35.3 times e to k times exactly. So when t is 10, a of 10 is 50.5. Okay, what am I solving for now? Exactly. This is what I don't have. K I don't have. However, the equation is not ready. It needs to be cleaned up. How do I clean this up? Excellent. Yes, of course. So 50.5 divided by 35.3 equals e to k 10 times k. Do not waste your time dividing. There is no need. So then what will we do next? There is only one thing we can do because the left-hand side and the right-hand side cannot be presented with the same base. And some people say 17 and 71 will be the same, but they're not. Sorry about that. I was looking at a problem with Ella earlier, and I said, whoa, why did you do this? And she said, but 71 and 17 are not the same. I said, oh, yeah, that's true. So only now we can apply natural log. Exactly. 50 divided by 50.5 over 35.3 equals 10k. But now I should write times natural log e. But we established last time that natural log e is exactly. That's why I won't write it.
Why is it?
Very good. Let's do this again.
Sorry.
No, that's fine. So we'll come back in a second. So let's say log base a of a is unknown. I have no clue what it is. But I know that I can change this into an exponential equation. A raised to which power is a? A raised to which power is a? Exactly. So that's the same reason why I have no idea what natural log e is. But I know that, what is the base here? I don't see a base.
No.
Okay. The 10 is for log. So what is the base for ln? There is no base of 1, right? E raised to which power is e?
1.
And it is 1.
Okay.
Because natural log has base e. E raised to which power is e? And the answer is 1. Okay, perfect. So from here, I will solve for k, dividing both sides by 10. So natural log 50.5 over 35.3. Be very careful how you put in the graphing calculator. This is crucial, please. So let's do it. So natural log, in parentheses, the parentheses pop up already. 50.5 divided by 35.3. Close the parenthesis and divide everything by 10. Because the denominator is just one term, you do not have to put that in parentheses. So please press enter. When we press enter, we get what? 0.058. And this is what again? Exactly. However, we cannot use percent. But yes, it's the growth rate, 0.0358. If you want, 3.58%. I have all the entire function now. 35.3 e to 0.0358 t. And now I can answer any question about it. This was part A. We determined the model fully. Part B. Use the resulting model to project the Hispanic resident population in 2015. What am I trying to do now? In part B, this was part A. I'm trying to find the, according to the model, if the model still held in 2015, then it will work and it will give us the population in 2015. So what do I have to do? Exactly, A of 15. So let's do that with the graphing calculator, please. So 35.3 times E, in parentheses, please, don't forget parentheses for the power. I'm going to call the previous answer and multiply it by 15 and close the parenthesis. So it appears that if the model still holds, 60.4 mil.
How did you do that answer?
Because I already had it in previously, so I didn't want to put it in. So second and previous answer. So second and minus. And multiplied, you have to put multiplication, I think, and put E. I don't think it works without the product. Maybe not. Okay, part C. In which year will the Hispanic resident population reach 70 million? Excellent. However, it's not cleaned up. It needs work. What do I need to do? Yes, I have to. So 70 divided by 35.3 equals e to 0.0358 t. Excellent. And what do I do next? I only have one choice. Say it again. Yes, I have no other choice but apply natural log. So natural log of 70 over 35.3 equals 0.0358 t. How come that I don't write multiply by natural log e? Because it's 1. So then t equals natural log 70 over 35.3. Careful how you plug it in, please. So natural log of 70 divided by 35.3. Close the parenthesis. There is no need for the denominator. You cannot recall the previous answer because you're not going to multiply by what you're not going to divide by what is needed. 0.358. And press enter. What does this mean? Exactly. So in 2019, which is this year, if the model still holds, the population is supposed to be 70 million. Say it again.
I find this a little confusing. It's,
Which part?
what we substitute, the not even that, more so like the, I guess plugging in the things like when we did A and 15, like for B. So we did A times 15. Right?
It's A of
A
15.
of 15.
Right.
Well, where'd you get 15 from?
The question is part B. It says use the resulting model to project the Hispanic resident population in 2015.
Also, you put the year in.
You told me to plug in 15.
I did. I don't know. So is A. All right.
So
A
when time is 15, A of 15 will be with 15 in here. $35.3 times E to blah 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 times 15. If this is 15,
Right.
this is 15.
Right. But what did we multiply? What was A?
We are determining it. We don't have it. We are determining the amount, the number of people 15 years later. 35.3 times e to raised to 0.0358 multiplied by 15, and we got this number.
Okay, so we put 15 into that equation right there.
Yes.
Okay.
Yes. Where t is.
Where t is for both of them.
No. Yes. I mean, this is just a number. Yes. The function when t is 15. And the answer was 60.4. Is this clear now?
Yeah, it's better.
Other questions, anyone? Yes. Okay, so let's take a look at another. With the exponential growth or logistic, or still exponential growth?
Yeah. Just like maybe not. Maybe I don't have to go through all parts of it, but just like
With the exponential growth?
yeah. What
Okay.
we just did.
Yes, very good. So let's do the, I'm looking at 26 on page 539. Let's read it. The function a of t equals 82.3 e to negative 0.004 t models the population of Germany, A, millions, t years after 2010 years. So what does 2010 represent? T equals 0. Good.
How is it 0? Is it
T years after 2010.
10? Okay.
Is that better? We don't have any information before 2010. So 2010 is the reference point. For someone born into, this is the idea was born in 2010. So that must be 0 years. For someone born in 2010, T is 0.
Because that's the origin.
Because it
Right.
says,
Originally.
yeah, because it says T is years since 2010. I cannot go back and refer it to 2000.
Okay.
I have to refer it to 2010. In this problem, in the previous problem, was the reference point was 2000, but here it's 2010.
How do you do a scale? You might have weight on it. Starting with these.
Like 0.
What was the population of Germany in 2010? That's our first question.
You don't have to do the math for that.
How do I determine that? Exactly. A of 0. So how much is 0 times negative 0.004? How much is e raised to 0?
1.
Right. So we knew that this is the population.
And then you multiply that times 1.
Because this must be a 0. Say it again.
So after you solve that part, it's all multiplication. So you multiply it times 1, whatever e.
Right,
raised-
because it's
okay.
to 0. Because it's raised to 0.
Okay.
So if
I see it. I just gotta write the steps down.
sure.
Then I-
So if t is 15, then I plug in 15, and this will not be 0. But if t is 0, 0 times negative 0.004 is 0, e to 0 is 1, this disappears because it's 1, and I get this. It's expected because this is the model.
Okay.
Now in part B, is the population of Germany increasing or decreasing? And you can say, I don't know. I only looked at A0, which is 2010. Let's look at another A. A 10 years. In other words, in 2020. Okay, perfect. So let's see what we get. Let's plug it in. 82.3 times E. In parentheses, what do I write? Negative 0.004 times 10 indeed, close the parenthesis, and I get 79 million. Maybe you didn't put parentheses, or you put the negative, not the small negative, but the big negative in parentheses. Yeah.
Oh, it's going in.
I think I did that.
Yes, that's why. Okay.
It's going in.
So it appears that it's decreasing. Very good. Part C. In which year will the population of Germany be 79.1 million? Disregard this, because we determined this just to see, if it's decreasing or increasing. So in which year the population will be 79.1? We can, I completely agree that's the assumption, but we have to show the work. So in which year is the population 79.1? What do I have to do? What do I write?